Welcome to all. Myself is Risha, working as assistant professor in MBR College of Engineering and Technology in Mechanical Engineering Department. So today we are going to discuss about, already we have discussed about the second law of thermodynamics in third unit. So we can recall. So what we uh, 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 continue the section in last previous class. So in last class we know about the topic of second law of thermodynamics. So already we know what is second law of thermodynamics. A process cannot happen unless it satisfies both the first and second law of thermodynamics. The first law defines about the quantity of the energy. So in first law, it defines about the quantity of the energy, while the second law defines the direction which the process can take place and its quality. So what is the meaning of that? In first law, we just say about heat is converted into work, work is converted into heat. So that is the first law of thermodynamics. In second law of thermodynamics, it gives the direction. So when how the energy transforms from higher body to lower or lower body to higher, so it gives the direction in second law of thermodynamics. So can take place and its quality. There are two statements defining the second law of thermodynamics. Already we discussed what are those two statements. One is a Kelvin Planck statement of second law, and another one is a Clausis statement of second law. Okay, then. Okay. So why you are discussed again? So in the last previous class, we just discussed about what is the second law of thermodynamics and how it is used to Kelvin Planck statement and Clausius statement and different systems. So in this second law of thermodynamics, the systems, which type of systems are used? One is heat engine, and another one is heat pump and refrigerator. So those are the examples for second law of thermodynamics. Uh, in heat engines, so now we start the topic of heat engines. Already we know the heat engine. So what is heat engine? So heat engine is a device which converts heat or thermal. So we can call heat or thermal energy to mechanical energy while operating in a cycle. So how it defines? So heat engine, it is a device. It is a device which converts heat energy to mechanical energy. So heat energy to mechanical energy while operating in a cycle. So the difference we called as a heat engine. Okay, now we look at this diagram. Now look at this diagram here. So this is the heat engine. Heat engine. This heat engine is a device which converts thermal energy to thermal energy to mechanical energy. So how it takes thermal energy? Already I told. So what I already told there. This is the thermal reservoir. This is a thermal reservoir. This is also thermal reservoir, but it maintains high temperature. It maintains low temperature. So this TH we called as a source. TL is called as we called as a sink. Sink. Why you called as a source and sink? Here source, our supply of heat. So which converts. So we have to supply heat. Then after it converts into mechanical energy, right? So here, this heat where we can take. So that heat we can take place from the source. So we take the heat from source. So when we take the heat from source, but it does not change. It does not change any of its temperature in the source. It maintains constant temperature when we take the heat, when we take the temperature. So that we call as a source. So we can take the heat from source. So, and this is up and this heat. So we called as so this is the TH called as source. So Q is the supply of energy. So that is the heat energy. We called as QH. This QH taken from source. So this heat is supplied to the heat engine. So heat is nothing but thermal energy. This thermal energy is supplied to the heat engine. This energy, this heat energy is converted into mechanical energy. So mechanical energy is nothing but we can do the mechanical work. So it gives the mechanical like shaft rotating, that is So it gives the mechanical. So we supply thermal energy and this converted into mechanical energy. And the rejected heat, that is called as QL. Supplied heat we called as QH and rejected heat we called as QL. This rejected heat is sent to the sink. Sent to the sink. So taken heat from source and the rejected heat is sent to the sink, and it is also absorb the heat from lower temperature, rejected heat. This rejected heat is absorbed to the sink, but it also does not change any temperature. It also maintains the constant temperature. So finally, what I want to tell you. So taken heat supply from source and sent to the heat engine, and heat engine were doing some amount of work, and finally it gives output as mechanical energy, and rejected heat is sent to the sink. So this overall we called as a heat engine. Here what is our net work done? Heat supplied minus heat rejected. Work done is nothing but difference of heat supplied and heat rejected. Here heat supplied is QH and heat rejected is QL. So finally net work done is equal to QH minus QL. So thermal efficiency. Why I want to tell all these definitions, because of we are going to solve some more problems regarding these heat engines, heat pumps and refrigerator. So that is why I'm telling this all these definitions and these formulas. So you remember everything this formula, and it is easy to understand, students. Okay, so net work done is nothing but the heat supplied minus heat rejected. Here heat supplied is QH and heat rejected is QL. And finally we are going to define the thermal efficiency. So thermal efficiency is defined as work done net divided by heat supplied. Okay, efficiency is defined as the ratio of work done net to heat supplied. What is our work done net? Work done is heat supplied minus heat rejected. So heat supplied minus heat rejected. So divided by heat supplied is QH. So QH by QH 1 minus QL by QH. So this is our efficiency is equal to 1 minus QL by QH is the efficiency of thermal efficiency of heat engine. Yeah, okay. So work done is QH minus QL. Thermal efficiency is work done net to heat supplied. Work done is QH minus QL by QH. Finally, thermal efficiency of heat engine is 1 minus QL by QH. Okay, and next Kelvin Planck statement. So in our Kelvin Planck statement, already we know what is the Kelvin Planck statement. Without sink. So here 100% of Q is converted into 100% of work done. Why? Because we did not supply any sink. So that is because of this reason Q is equal to H. So whatever the amount of heat is given to the engine, and that much of amount given to the that much of the amount. So work done given by the engine. So QH is equal to W. So finally our efficiency is 100%. But in our real cases, 100% efficiency is not possible. So definitely it violates the second law of thermodynamics. Here the Kelvin Planck statement violates the second law of thermodynamics. It states that it is impossible for any device that operates on a cycle to receive heat from a single reservoir. So it is not possible to receive heat from a single reservoir and produce network. So it takes receive heat from single reservoir and use the work done. It is not possible. Okay. So in other words, it is impossible to build a heat engine with 100% efficiency. So in our heat engine, it does not use the 100% thermal efficiency. So our device, it violates the second law of thermodynamics. So that we called as a Kelvin Planck statement. So a heat engine has to reject some energy into a lower temperature sink in order to complete the cycle. So if you put the sink, it rejected heat to the sink. So when we put the sink, at that in order to complete the cycle. Otherwise our cycle is no our cycle will not complete. Okay, the higher reservoir temperature, the higher the quality of energy, and more work is produced. So if you supply the higher quality of energy and more work, so if you supply the lower quality of energy, it will not give the high much amount of work. It gives some losses because of your quality. Your quality is not maintained. So if you maintain the quality of energy, maintain very good, it gives more work is produced. And next, this statement does not have any proof. So this does not have any proof, and it has not been violated at. So this statement has not any proof because of our cycle will not completed. So if it is not completed, if it will not complete the cycle, so complete the cycle, how we can take run the system? It is not possible. It is impossible. So our the statement does not have any proof, and it has not been violated. So our Kelvin Planck statement violates the second law of thermodynamics. And next, heat pump and refrigerator. So in heat pump, how to take heat pump? This is heat pump or refrigerator. Here the procedure is same for heat pump and refrigerator. Both procedures is same. Heat pump and refrigerator procedure is same, but the only one thing is desired effect is change. So how will take desired effect to both of them? A heat pump is defined as a device that transfers heat from lower temperature lower temperature to a higher temperature one. Example heat. Sorry. Example, a heat pump is used to extract energy from outside and cold outdoor air to the warm indoors. A refrigerator performs the same function. The difference between two is in type of heat transfer that needs to be optimized. Actually, here when actually the main difference between heat engine and heat pump and refrigerator, in a heat engine it gives a work done by the system, but in our heat pump or refrigerator work done on the system. So we will supply the energy to the heat pump or a refrigerator. Then after it will take temperature from sink to source. So otherwise it will not take any temperature from sink. Okay. When we supply the work to the heat pump or refrigerator, then after it will take heat supply from sink. Afterwards it supply to the source. So that is the main difference between the heat pump, refrigerator, and the heat engine. So this is a heat pump or refrigerator. When we supply the work done, and the heat received from sink, then after rejected to source. Here heat received from sink. Okay, here heat received from sink and rejected to source. Okay, in a heat engine, heat received from source and rejected to sink. So this is heat engine. In um, in heat pump, heat received from lower temperature and rejected to higher temperature. Okay, so heat pump is defined as a device that transfers heat from a lower temperature source to higher temperature one. A heat pump is used to extract energy from outdoor cold air to warm indoors. So here, if you consider only heat pump, our desired effect is happened in a source. If you consider only a refrigerator, our cooling effect will takes place in lower temperature. Why? Because refrigerator means we want cooling effect. So here what we do, we should heat from sink. So here we are take off the heat from the sink. That means it cools. So here if we take only refrigerator, so we want cooling effect. Our cooling effect, our desired effect here only. So our desired effect for refrigerator is TL. And if you replace heat pump, we want heat pump is used to extract energy from outside cold door air to warm indoor air. So here if we replace heat pump, we have the desired effect of heat pump here, so that is TH. So if you want a refrigerator for desired effect is TL and heat pump desired effect is TH. That is the main reason. After that, the procedure of a heat pump or refrigerator both are same. So our refrigerator desired effect is TL, our heat pump desired effect is TH. Okay, and next heat pump and refrigerators. So here heat pump and refrigerators. So the efficiencies of heat pump and refrigerators are denoted by the quotient of performance. In the main difference between the heat pump, refrigerator and heat engine. In heat engine, we are considered thermal efficiency work done to heat supplied. But here we are also here take the thermal efficiency, but we replace efficiency with the quotient of performance. In heat pumps and refrigerator, we will consider quotient of performance that is in the short form of COP. So COP we call as quotient of performance. Where for a heat pump, for a heat pump, COP of heat pump. So here heat is supplied to work done net. So in our thermal efficiency, work done net to heat supply, but COP is equal to heat supplied to desired effect. Already I told you students. Already I told you. So what is the what where is the desired effect we get? So where is the desired effect we get? So here in heat pump, we desired effect we get TH. That is nothing but QH. And where is the desired effect here? Q for refrigerator, that is QL, that is TL. So uh, so our heat supply, our QH by W net. So QH by W net. So sorry, desired effect to work done. Here directly given the QH. So quotient of performance is defined as the ratio of desired effect to work done net. Okay, remember one thing. Our quotient of performance defined as desired effect to work done net. Here our heat pump desired effect is QH. In our heat pump, desired effect is QH by work done net is same. So work done is the same for heat engine and heat pump. So both we are getting the same internal work done net. So QH by QH minus QL, that is 1 minus 1 1 by 1 minus QL by QH for heat pump. Here for a refrigerator, desired effect to work done net. So in refrigerator, what we get cooling effect is our desired effect. So QL by W net. W net is nothing but QH minus QL. So finally we get 1 by QH by QL minus 1. So this is a quotient of performance. Quotient of performance defined as the desired effect to work done net. For heat pump, desired effect is QH. For refrigerator, desired effect is QL. Okay, here the COP of heat pump is quotient of performance of refrigeration plus 1. So here quotient of performance of heat pump is greater than 1. So heat pump of quotient of performance heat pump is greater than quotient of refrigeration. So quotient of performance of heat pump is equal to quotient of performance of refrigeration plus 1. So quotient of performance of HP is always greater than 1. Next topic is equivalence of Kelvin, Planck and Clausius statement. We know that two statements of second of thermodynamics, that is Kelvin, Planck and Clausius statements. These statements may appear to be unconnected to each other at first glance, but it can be easily shown that they are virtually two parallel statements of second law, which is exactly what is proved in equivalence of statements, by showing that violation of one statement implies the violation of a second. So what is the equivalence is nothing but, so both are taken from the second law of thermodynamics. So at first glance, both are unconnected, but the both two statements are parallel to each other. So we take the two statements and exactly we are going to prove. So that is the equivalence. So that is same parallel statements. So two statements are parallel of second law of thermodynamics. So that is which is exactly which we proved in equivalence of statements by showing that violation of one statement implies the violation of second. So if you observe the diagram you can easily understand. So here hence there will be two possibilities for the system. So what is the first possibility? Violation of Clausius statement leads to violates a Kelvin Planck statement. So if you take Clausius statements, it leads if you take Clausius statement, it leads Kelvin Planck statement. If you take Kelvin Planck statement, it leads Clausius statements. Okay, so that is both are parallel to of second law of thermodynamics. So if you take violation of Clausius statement, what is the violation of Clausius statement? Without supply of work done, without supply of work done, the it didn't heat takes place from lower to higher. So it is not possible. Okay, if you give not any power supply to the motor, is it possible to pump the water to water tank? It is not possible. If you supply the work, if you supply the power, it transfers the water from one state to fourth state. So it is possible when we supply the electric power. So that is possible. If you do not supply any electric power, how it is possible the motor pump moves from one state to fourth state? It is not possible. It is not possible. If you want to give some supply of energy, supply of power, it works. After that it is not work. It is not work. So at the same way here also, in Clausius statement, if you do not supply any work done, it does not takes place, heat transfer takes place from lower temperature to higher temperature. So that we called as Clausius statement. The Clausius statement violates the second law of thermodynamics. So here we consider violation of Clausius statement. So what is a Clausius statement? This is Q1 and this is Q1. So this is heat pump. So this is heat pump and this is a heat energy. This is heat pump and heat energy, right? So what is our heat pump? We want to supply heat from Q1 to Q2. Q1 to Q2. So it violates the second law of it violates Clausius statement. Why it violates Clausius statement? Because here we do not supply any work. So it violates a Clausius violation of Clausius statement. But it leads the it violates Clausius statement. It violates Clausius statement. So here we can observe. So it takes the heat from hot reservoir and runs the heat engine and gives the work done and remaining supplied to the cold reservoir, right? So so here what we should do. So this is the violation of Clausius statement. If we and next we go to violation. What is the violation of Kelvin Planck statement? Actually, we take the heat supply and run the engine and gives the work done, and this total work is given to the heat pump and it runs the and it runs the heat pump. It runs the heat pump. But here we supply only one thermal energy reservoir. Here we supply only one thermal energy reservoir. So if we supply only one thermal energy reservoir, it violates the Kelvin Planck statement, right? It violates the Kelvin Planck statement. But we can observe one thing. Here. Here we do not supply any energy, but only the Q1. Only the Q1 is supplied to the hot reservoir and takes Q1 and runs and runs the heat engine, gives the work done. So here it violates of Clausius statement, but it leads to Kelvin Planck statement. That is the point A. It is a violation of Clausius statement, but it leads to Kelvin Planck statement. It is a Kelvin Planck statement, but it leads to Clausius statement. The work is given to the heat pump. Work is given to the heat pump. It violates the Clausius statement. Violation of Planck statement and leads to the Violet's Clausius statements. Right. So that is the meaning of that. So violation of Clausius statement leads to violation of Violet's Kelvin-Planck statements, and violation of Kelvin-Planck statement leads to Violet's Clausius statement. Okay. This is the Clausius statement. This is the Clausius statement, and this is the Kelvin-Planck statement. So Kelvin-Planck statement violates the Clausius statement, and Clausius statement violates the Kelvin-Planck statements. That is the meaning of that. So there will be two possible for the systems. Here also the same thing. Violation of Kelvin-Planck statement. So what is the violation of what is the violation of Kelvin-Planck statement? If we run with only one thermal energy reservoir, it gives 100% thermal efficiency, that we call as Kelvin-Planck statement. So that is meaning of that. Let us assume heat engine violates Kelvin-Planck statement. That is, it works with 100% efficiency. There is no heat loss. Now we take a heat pump which follows Clausius statements, which extracts heat from cold reservoir and transfer to hot reservoir at high temperature with expenditure of work equal to what is provided by heat engine. Here, heat pump in heat engine together constitute a heat working pump in a cycle whose sole effect is transfer heat from lower temperature to higher temperature body violating Clausius statement. Here heat engine and heat pump together constitute a heat pump working in a cycle whose whole effect is to transfer heat from lower temperature to higher temperature body violating Clausius statement. Okay, so here it is a Kelvin-Planck statement. This is so this is violation of Kelvin-Planck statement. In this Kelvin-Planck statement, so takes heat from reservoir and it works, and this work done is given to the heat pump. So heat pump. So also we called as this is the violation of Kelvin-Planck statement. Okay, so this is the violation of Clausius statement. What is the Clausius statement? Without supply of work done. So that we called as the Clausius statement. Okay, this is the combined system Q2. So Q dot net is equal to Q1 plus Q2 minus Q1. This is Q1, so supplied work done. So because taken work done from heat engine and its heat supplies from Q2 to Q1 plus Q2. So what is our finally work done? What is our work done? Q1 plus Q2 minus Q1 out. So this is a violation of Kelvin-Planck statement. So just so what is the equivalence between both are parallel statements of second law of thermodynamics, is nothing but equivalence. And here violation of Clausius statement is without supply of work, that we called as Clausius statement. Without taken only single reservoir, thermal energy reservoir, that we called as violation of Kelvin-Planck statement. Both are parallel of second law of thermodynamics, so that we called as equivalence of Kelvin-Planck and Clausius statement. So just you have to remember these formulas only. So what are formulas? What is the COP of what is the what is the thermal efficiency? Here work done by heat supplied, that is the thermal efficiency of heat engine, and COP. So those formulas are very important. And next class by taking these formulas and now go, and next class we will do some problems related Kelvin-Planck statement and Clausius statement. And so those are all the two statements for second law of thermodynamics. And heat engine, heat pump, and refrigerator. By taking these systems, the next class we will do some problems. Okay, so we have just remember what is thermal efficiency of heat engine. So efficiency of heat engine is work done netted by heat supplied. And next, quotient of performance. In heat pump and refrigerator, we will consider only quotient of performance. So quotient of performance of heat pump is discrete effect by work done net. What is discrete effect of heat pump? QH. And refrigerator, discrete effect is QL. So those are all the formulas regarding the heat engine, heat pump, and the refrigerator. And next next class we will do some problems uh, related to heat pumps, refrigerator, and heat engines. Okay. Thank you, students.